Welcome guys. In this video we are going to look at calculations associated with the array diagrams. Now we did a video where I focused on how to draw a array diagram depending on the position of an object with respect to length. Now before we start our lesson, I just want to remind you guys that my online classes are still on, and I have a simple promotion where I'm allowing you guys to pay a 50 kwacha per subject, and if you want to maybe make some inquiries or make payments, you can contact me on this line. For those that wish to make payments, it's under the name Isaac Machiko. So now let's begin with our lesson. Now before we start our calculations, first let's begin by looking at a array diagram. So the first line that you are supposed to draw under array diagram is known as the principal axis. Then I'm going to draw my convex lens in the middle of this line. Now when you are drawing these kinds of diagram, please make sure you use a rule. Right, now the point where the line is cutting or meeting the lens is known as the optic center. Then at this point where the rays of light can pass through is known as the focal point. The distance from the optic center up to the focal point is known as the focal length. So even here we may have another focal length, and the focal length must be equidistant. Now let's look at we place an object on this point. So an object is placed on the left side of our lens. So this is our object. Then the distance from the center, the optical center, up to where an object is placed is known as the distance of an object. And we use DO to represent this. Then let's say we have an object, an image, let's say formed upside down on the other side of our diagram. The distance from this optical center up to where the object, the image is known as distance of an image, denoted by DI. Now, apart from knowing this, the other thing that you are supposed to know is the height of an object, so HO. Then the height of an image is HI. Now, the first formula that you are supposed to know for the thin lens equation is this one, 1 over F. F is for the focal length is equal to 1 over DO, which is the distance of an object, plus 1 over the distance of an image. Now from the calculations, you can tell if the image is real, virtual, upright, or upside down, inverted or non-inverted. So let's first begin with if the distance of an image is let's say negative. So if you calculate and find the distance of an image to be negative, then you can conclude by saying the image is virtual. Virtual simply means not real. If the distance of an image is positive, then you are dealing with a real image. Now apart from that, we can also look at the height of an image. If the height of an image is negative, then it simply means that the image is inverted. What do we mean by inverted? So inverted simply means that the image is facing upside down. So you need to remember that. But in a case where we have the height of an image to be positive, then this simply means that the image is facing upright. Then the second formula is magnification is equal to height of an image divided by height of an object is equal to negative di divided by positive do. Now let's look at an example. So let's say we have a ray diagram with the focal length of 6 centimeters, then a distance of an object we can say is just 8 centimeters, then the height of an object is let's say 2 centimeters. Now we are going to first begin by we are going to find the distance of an image. So remember the formula is 1 divided by f is equal to 1 over distance of an object plus 1 over distance of an image. So we can now do the substitution. So I can say 1 over the focal length is 6, 1 over distance of an object is 8, plus 1 over distance of an image. So if you want, you can shift this 1 over 8 to the left side, because our target is to solve for di. So what I'm going to do, I'm going to get rid of the fraction. So I'm going to multiply by the common denominator. So the common denominator by 6 and 8 is just 6 times 8, which is 48. But instead of writing 48, I'm just going to write 6 times 8 times di. So as you can see, I'm multiplying everything by this part here. So I'm going to distribute. So I'm going to say 6 times 8 times di times 1 over 6. So if you look at this mathematically, it's same as 1 over 6 times 6 times 8 times di. So I can just cancel the 6. So you've seen the importance of y. I'm just leaving the numbers like that. So I can cancel the 6, which simply means that I'm going to have 8 di. Number 2, we get this, we multiply by this one. So if I cancel this one, I'm going to have 6 di plus, if we multiply this times this, the di will cancel, giving us 6 times 80 will give us 48. Then I'm going to shift 6 di to the left side, giving us negative 6 di is equal to 48. Then 8 di minus 6 di, we get 2 di is equal to, here we have 48. If you divide by 2, then our di is just 24. So which means that if the distance of an object is 8 centimeters and the focal length is 6 centimeters, then the distance of an image is 24. So we can see that if we are to move from 8 to 24, we can just say 24 divided by 8 is giving us 3, which simply means that the distance of an object was multiplied by 3 to give us 24. Now let's maybe have this as now the diagram. So let's look at how can we put this information on a diagram. So as usual, you first need to begin by drawing a principal axis. Then here I'm going to put my lens. So remember, if let's say we put our focal point number 1 here, and let's say we put our focal point number 1 on the other side here. So remember, the distance from here up to here, which is the focal length, is 6 centimeters. So the 6 centimeters is here. Now whatever the distance of an object is 8 centimeters. So if it is 8 centimeters, then our object is placed beyond F, because this is where we can assume the distance of an object to be 8 centimeters, since here up to here is 6 centimeters. So please take note of that. Then I'm going to now draw the first ray of light parallel to the principal axis. Then upon touching the center of our lens, we are going to bend and pass through the focal point number 1. So make sure I use a rule when drawing these lines. Then number 2, I'm going to draw another straight line passing through. So passing through the optical center. Right, then I'm going to draw another one passing through here. Okay, let me not include the second one, it's okay. So the point where these lines are meeting is where the image is likely to form. As you can see, the distance of an object is given in the question is 8 centimeters. Then from our calculations, the distance of an image is 24 centimeters, and we can see that the distance of an image is greater than the distance of an object. Now from this, we saw that the distance of an image is positive, which simply means that the image is real. Now let's look at the height of an image. So the height of an image, we can first find the magnification. So magnification is equal to let's say negative, so distance of an image over the distance of an object. So is equal to negative, what is the distance of an image is 24 over distance of an object is 8. So negative times 24 is negative 24 over 8, which is giving us negative 3. So the negative is there telling us that the image is facing downward. So then the number for magnification is absolute, so we just have to focus on the positive side. So it simply means that the distance of an image is 3 times the distance of an object. So if we get, let's say 8, we multiply by 3, we get 24, which is our final answer. So if the magnification is 3, then this simply means that even the height of an image will be 3 times the height of an object. Now let's look at the height of an object. So the height of an object is equal to 2 centimeters. So the height of an image will be 6 centimeters. Now where is this 6 centimeters coming from? We can say magnification is equal to HI over HO. So the magnification is 3. Negative 3 is equal to HI is what we are solving over 2 centimeters. So if we say 1 over, we cross multiply. So 1 times HI, we'll get HI is equal to 2 times negative 3 will give us negative 6 centimeters. So if the height of an image is negative, then it simply means that the image is inverted. It simply means that it is facing downward. Now let's have an example, another example. So let's say we maintain the same focal length, we say 6 centimeters. Then the height of an object still 2 centimeters. But let's change the distance of an object. Instead of 8 centimeters, let's say we use, let's say 4 centimeters. So the first step, number 1, let's find the distance of an image. So as usual, I'm going to use the Finn's length equation when 1 over f is equal to 1 over di, meaning 1 over do plus 1 over di. So 1 over 6 is equal to 1 over do. Do is the distance of an object, this time is 4, plus 1 over di. So I'm going to do the same. I'm going to multiply by 6 times 4, which is 24. Now we know that we can use 12 because 6 and 4 can go into 12. So I'm just going to say 12 di. So I'm going to distribute 12 di times 1 over 6. So this is same as 1 over 6 times 12 di. So we can say 6 here 1, 6 here is 2, which simply means that 1 over 6 times 12 is just 2. So I'm going to say 2 di. Then we have the second one, 1 over 4 times this is same as 12 divided by 4, giving us 3 di, plus di, 1 over di times 12 di, the di will cancel, giving us 12. Then I'm going to shift 3 di to the left side, giving us negative 3 di. Then here we have 12. So we are going to have negative di is equal to 12. We divide by negative, divide by negative. So di is equal to negative 12, which simply means that the distance of an image is negative. Now, if the distance of an image is negative, what conclusion can you make even if you do not have a diagram? So the conclusion that you can make is that the image is virtual, it's not real. Now, let's say maybe we look at this diagrammatical way. So I'm going to first begin by, I draw my principal axis. Then I put my convex lens here. Remember, the focal length is 6 centimeters. They have to be equidistant. Now, if you look at the distance of an object is 4 centimeters, and from here up to here is 6. So the 4 centimeters, it simply means that the object is between F and the lens. So let me put it somewhere here. So if we, let's say, draw a parallel line, the principal axis, then another one passing through the center. So if you look at these two rays of light, on this region here, they are spreading apart. So now, what we do is now, you draw a dotted now going backward. The reason why it's dotted is because it's in actual sense, it's not real. It's just like imagine. So if we were to draw backward, the rays of light may seem to meet at this point. So as we can see, this is now our image, and it's virtual because it is on the same side. So we have seen that the calculation has obeyed with the diagram. So we can now say the distance of an object was given is 4 centimeters. Then the distance of an image is 12 centimeters, which is negative 12 centimeters. Okay, if this is the case, let's find the magnification. So magnification is equal to negative di divided by the di, I mean do, distance of an object. So negative, what is the distance of an object is negative 12, centimeters over DO is just 4 centimeters. So negative times negative, we have positive 12 over 4. Let me just cancel the centimeters. So 4 into 12 is 3. So as you can see now, our magnification is positive. When the magnification is positive, then you are dealing with a virtual image. So you can use the distance of an image and the magnification under calculations to tell if the image is real or virtual. Now, what of the height of an image? So we are going to use this formula. Magnification is equal to HI over HO. So the magnification is positive 3 HI over HO is 2 centimeters over 1. So if we multiply 2 times 3, we'll get positive 6 centimeters. Remember, in the first question, the HI was negative 6, showing us that the image is facing down. Now, since the HI is positive 6, then it simply means that the image is on the same side and facing upright as the object. So we've seen how the calculations have obeyed with the visual representation. So we have 6 centimeters, then here we have 2 centimeters. So the height of an image is 3 times the height of an object. The distance of an image is 3 times the distance of an object. So this is how you have to deal with calculations connected with the ray diagram. So that's it for this video. Thanks for watching.